Yeah, so Assalamualaikum and good morning. Okay, so we already finished the first chapter of your KNR1073, electrical instrumentation, the first part of the understanding of the measurement and also uh, the calculation of the deviations and everything. Okay, so related to errors and so on. So for this week, I will teach you again on the theory behind the indicating instruments. So as you all know, we have two type of instrument. We have analog instrument and also digital instruments. Okay, so I think I will finish all the lectures by this week, and then we'll give you some exercise and we'll discuss on the exercise for the following week before I give you to Dr. Lisa, no, Mr. Hazmi for the second part, which will start around week 5. Okay, so next week will be week 4. I will give you exercise also, and then we will discuss again on your some of your friends punya proposal. Okay, is it okay for you? So you can type on the chat.
Yes, madam.
Yeah, so we need to finish the lecture so that you can prepare yourself for the test one later. Okay, so the the main thing for this chapter is just a theory behind. Okay, so indicating instrument is a very important instrument. It's a conventional instrument and also is the basic instruments that you need to know before you move on to digital instruments. Okay. So this is the notes is already uploaded in the ellipse and also some exercise for you to do later. Okay. For the calculations activities, I will discuss maybe if we have time today, or maybe we can discuss it on Thursday and also the following week. Okay. So maybe some of the class will be I put a recorded, depend on the availability lah. Okay. Later we will do for you.
Doctor,
Yes.
how about the answer for the previous exercise?
Okay, we'll discuss again for if we have time today or maybe on Thursday.
Okay.
Okay, so for this topic, you will learn all the theory behind what is the fundamentals of deflecting instrument. So you need to remember all the three forces that is important in the instrument. So first we have a deflecting force, then we have a damping force, then we have control force. So all these three forces must be exist when you do the measurement in a specific instrument. Okay, and then we need to learn on the PMMC, or what we call as the D'Arsonval instrument construction, and then galvanometer, adjustable shunt resistor, types of instrument, and also deflecting meter movements, AC and DC errors, and moving iron repulsion. So this is all the theories only. For this topic, they will not have any calculation. So what is the fundamentals of deflecting instrument? So what does it mean by deflection instrument? Okay, so deflection instruments meaning that anything that can deflect the pointer. Okay, so makes your pointer move from a 0 point to a measured point. Okay, so this pointer you need to calibrate it before you need to do your first measurement. Okay, so this pointer will indicate the measured quantity. Either you want to measure the current, the resistance, or the voltage. Okay, so depend on what type of measurement that you want. Okay, and then for this to occur, we need to have three different type of forces that need to occur simultaneously. First, you have deflecting force. Okay, deflecting force is for you to be able to move your pointer from 0 point to a specific point. Then we have a controlling force that control what is your end of measurement, what they control the deflection of your pointer. And then we have a damping force, which is to control the stop of your measurement. Okay, so these three forces must be exist in the instruments itself. Okay, so this is how it looks like for the deflecting force. Due to the existence of the electric and magnetic field interact between the two different type of magnet, they provide a deflect force to your instruments. Okay, so it causes the pointer to move from its zero position. Okay. In permanent magnet moving coil, the deflecting force is what we call as the magnetic force. Okay, and then when a current flows in a lightweight moving coil pivoted between poles of permanent magnet, so this is why the deflecting force occurred in the instrument itself. Okay, so the current sets up a magnetic field that interacts with the field of the permanent magnet. So try to remember the figure of the deflecting force. Okay, so the deflecting force, they follow what we call as the right hand rules. Okay, so this one, the rules you will learn on the circuit theory later. Okay, so you can see that when you follow the right hand rules, your thumb will point on the directions of current flow, and then your fingers will point in the directions of magnetic field, where your middle is your current carrying wire, as you can see here. Okay, so in this figure, we have north to south. So this, every deflection instruments, they have what we call as the magnet. So we have north magnet and also south magnet. Okay. So the flow of the field flux can be determined by using the right hand rule. Okay, so this one. So from here, this one, the forces will pointing up. So you take your right hands and you turn it, then you can see that this is the flow of your magnetic flux flowing your fingers point. And then you put your right hand down. Okay, so this is your fingers pointing at this direction. Okay, so this indicates the flow of the magnetic field. Okay, so a force is exerted on a current carrying conductor situated in a magnetic field. Okay, so due to the existence of the force between north and south magnet, it will produce what we call as the magnetic field. So the existence of the magnetic field will make your pointer to deflect. Okay, so this is the first part of your measurement. So after that, we have what we call as the controlling force. Okay, so the controlling force must be exist the same with the deflecting force. So the amount of controlling must be the same with the amount of deflecting force, so that your reading is accurate. Okay, so the controlling force, you can see from the figure, is occur when where there is some measurement, and then it will be controlled by what we call as the spring balances. Okay, so this spring will balance how the reading being made and how the force being exists during your reading. Okay, so due to the existence of the controlling force, your pointer will not will start from the zero position until a certain value where your deflecting force equals to controlling force, then it will stop. Okay, so this is how the controlling force occurs. Then we have a damping force. Okay, so damping is what we mentioned as oscillation. So you need to minimize the oscillation of your uh, pointer, meaning that getaran dia lah. Okay, so kalau when you move from here to here, you need to have some sort of low oscillation so that you can have at the end, it will stop to and then give you the answer of your measurement. Okay. So damping force is caused by the what we call as the uh, eddy currents relationship between the magnetic field and also the intersections of the conductor. Okay, so the damping force is used to minimize the oscillation. Maksudnya dia akan kurangkan the getaran of your pointer. So makin banyak getaran, meaning that you cannot get the accurate answer. So that for the damping force to occur, you need to have a minimized oscillation and minimize the getaran. Okay. So in PMC instruments, this force is normally provided by eddy currents. So eddy currents will set up a magnetic flux that oppose the coil motion, thus damping the oscillations of the coil. Okay, so this is how it looks like for the eddy current. Okay, so here you can see your current from A to point B. So this is where your coil magnetic fields occur. And from here to the existence of your conductive material, this is where the eddy currents occur. And from here also, we know that the eddy currents is can produce both the magnetic field. So the induction of the magnetic field will produce and give you some results of your current later. Okay. This is the video dia macam on the eddy current. So any question? So for this for this type of lecture or type topics, it's just a theory only. So I give a video on what is eddy current. I need to stop sharing first. Okay, so this is the eddy current.
The word eddy literally means a circular current. Let us now try to understand how they are produced. Take a solenoid that has a soft iron core. Now connect this solenoid to an AC source. When a metallic disc is held over the cross-sectional face of the soft iron core, the metallic disc will be thrown into the air. When current flows through the solenoid, magnetic flux linked with the solenoid increases from 0 to finite value. This change in magnetic flux gives rise to induced currents in the disc. The upper face of the soft iron core attains the same polarity as the lower face of the disc. Hence, the disc is repelled by the soft iron core and is thrown up in the air. This experiment shows that when a conductor is kept in a changing magnetic field, currents are induced in the body of the conductor. These are currents that occur in very small loops and are called eddy currents. Foucault discovered eddy currents in 1895. In some cases, the eddy currents may produce undesirable effects. For example, they increase the internal energy and therefore can increase temperature of the material. For this reason, devices like transformers, which are constantly subjected to to changing magnetic field are often laminated, or their metallic core is divided into thin sheets. Each of these sheets are insulated from one another. The magnitude of eddy currents is given by I is equal to minus 1 by R into d phi v by dt. The direction of eddy currents is given by the Lenz's law, or Fleming's right-hand rule. Lenz's law states that the direction of induced current is such as to oppose the very cause producing it. Fleming's right-hand rule. Stretch the forefinger, the middle finger, and the thumb of the right hand such that they are mutually perpendicular to each other. If the forefinger indicates the direction of the magnetic field, the thumb indicates the direction of motion of the conductor, then the middle finger indicates the direction of induced current in the conductor.
Okay, so that one is the eddy current. So you don't need to bother about all the rules here. So the rules will be learned to you when you do the calculation in the circuit theory course later. Okay. This is another video for you. Okay, so from here you can see that the video doesn't have any sound. When it moves from north to south, just what I mentioned just now, the rotation, deflects and everything. This is inside the simplest example is with the multimeter at the lab, the analog multimeter, the one that will be used to do the calculations of the measurement of the currents. Where the three forces occur. First is the deflecting, second is the controlling, and then the end with the damping forces. Okay, so that one is for the permanent moving coil electrical setup. Okay. Okay, so as you can see here, so how does it looks like with the damping forces? If you have a lack of damping forces, will cause the pointer to have problem during their punya oscillations. Okay, so you can see here, this is how it looks like on the graph on the pointer oscillation with no damping. Okay, so this one is with damping, and this is where the positions of the pointer and the final pointer position. Okay, so lack of damping will cause the pointer to oscillate. So if the pointer oscillate, meaning that the reading cannot be collected at specific number of time. Okay, and then we have this is how the damping force in the PMMC instrument that can be provided by an eddy currents. Okay, so how it control the movement from the magnetic field of the north and also south pole of your magnetic and also of your measured devices. Okay. So bear in mind, we have two methods of supporting the moving system of a deflection instrument. So this movement can control the uh, oscillation and also the damping force for you in the instrument itself. Okay, so we have jewel bearings and also the taut band. So this is all the two methods. Okay, so this is the jewel bearings. Okay, so taut band suspension use no bearings. Okay, so this is the specification in the setup of the devices. Inside that, you need to put the jewel bearing here. Okay, so it supports the coil on a tiny flat spring at each end. So it support from here to control the oscillation. And then the flat spring act as both suspension and restoring force, as well as providing the current to it to the coil itself. Okay. So this is also a pivot and also jewel bearing suspension. As you can see how it looks like for clearer version. Okay, so here is you punya pivot and also jewel bearings. Okay, so the pointed ends of shaft or pivots fastened to the coil inserted into cone-shaped cuts in jewel or sapphire or glass depend on the types of the instruments. Okay, so this will allow the coil to route freely with the least possible friction. It will rotate inside this one with a small area here to control the movement and also the damping forces. So some jewel bearings are supported to absorb such shocks more easily. Okay. So this is another one. You use a taut band suspension instead of using the sapphire or glass or the jewel bearings. They put a taut band. Okay, where at the end of each of the taut band we have a spring. Okay, so the taut band method is much more sensitive because the spring will control and will produce a rubber under tension to the measured value of the devices. Okay, so the ribbons also exert a controlling force as they twist and they can be used as an electrical connections to the moving coil. So this is the looks like of the taut band. Okay, so here you can see the constructions of the PMMC devices. We have a permanent magnet with two soft iron pole shoes. Okay, so we have this is the shoes, what we call as the pole shoes. Okay, here we have a permanent magnet, and then you can see that we have a very narrow air gap between the core and also the facets of the pole shoes. Okay, so the narrow of the air gap will produce the less friction of your measurements later. Okay, and then we have a pivoted lightweight moving coil is pivoted to move within these narrow air gaps. Okay, so you can move, it will be makes your movement of the pointer. Okay. And then the narrow air gap is used to have a very strongest possible level of magnetic flux and also to control the movement of your pointer itself. Okay. And then we have what we call as here This one, when you see a analog multimeter, you can view this type of characteristic where this can be adjusted, the middle one, so that your pointer will start at the 0 point. Okay, so this is also to control and also to fasten the movement of your spring. Okay. Okay, so we have also what we call as the pemberat. Okay, so pemberat, which is the counterweight. Okay, so it will provide the mechanical balance of the moving system so that there is no gravitational effect on the accuracy of the instrument itself. Okay, and then sometimes they can have 2 or 3 counterweights attached to the pointer. Okay, so dia tak boleh berat sangat and dia tak boleh ringan sangat, and the functions is to control the movement of the pointer. Okay, so how does it looks like for the magnet? Okay, so this is the side view of the magnet. You have a soft iron cylinder. We have the permanent magnet. Okay, so in between we have a very narrow gap. Okay, so this will make a magnetic flux to flow in this gap. Okay, and then move within the narrow air gaps itself. Okay, so a major advantage of this type of core magnet type of construction is that the moving coil is shielded from external magnetic fields due to the presence of the soft iron cylinder. Okay. So the current, as you can see here, the current in the coil of a PMMC must flow in one particular direction to cause the pointer to move positively from the 0 position. Okay, so when the current is reversed, the interaction of the magnetic flux from the coil with that of the permanent magnet will cause the coil to rotate in the opposite direction and the pointer is deflected to the left of 0. So you need to check your devices. Either it is a positive calculation or you can have a center 0 where you can get the calculation of the positive or negative. So meaning that kalau you have a positive equipment or positive multimeter, when you put your props to measure the current, if your pointer deflect negatively, so meaning that your technique is wrong lah. Okay, so you need to have a positive directions only, one particular direction. Okay, so the terminals of a PMMC are identified as positive and negative to indicate the correct polarity for connection, and the instrument is said to be polarized. They have a value lah, determinate value. And then because it is polarized, the PMMC instrument cannot be used directly to measure alternating current. So this type of instrument is only able to measure a DC instrument or DC currents, the direct current only, where you can have you want to calculate the voltage, the resistance, or the current for the direct instruments. It's not alternating. For you to measure the alternating current, you use a oscilloscope. Okay, so the current will look like, instead of one straight line, is either sine wave or either cosine wave. So later, you will learn also the theory in the lab of KNR1042 for the measurement and instrumentation. Okay, so we learn on the measurement of a DC electrics, DC instrument, and also the AC current vector. Okay. So this is what I mentioned just now, where this device, they have positive and also they have negative. So depend on you where you want to put your probe. So if you want to get a positive value, try to use a positive from one point to another point where we can get a positive data. So if your probe is vice versa, so you have a negative value. So galvanometer, they can give you a positive or either negative value. Okay, so this type of instrument is a very sensitive instrument. Okay, so the deflection system is arranged so that the pointer can be deflected to either right or left of the 0 point. Okay, so this is how it looks like inside the galvanometer. So instead of using a pointer, okay, so macam jarum panjang tu, you use what we call as the mirror. Okay, so we have by using a deflection from the mirror and also the light beam from a mirror, you can get your result. Okay, so we have for this type of instrument, it can reduce the lowest possible minimum and also they have a very good sensitivity. Okay, so the weight of the pointer sometimes can create a problem in the original BMMC devices. Okay, so they just use a mirror and also the light beam to calculate the measurement. Okay. And also we have the light beam behave as a very long weightless pointer, which can be substantially deflected by a very small coil current. So this makes light beam galvanometer much more sensitive to lower current levels than the pointer instruments. Okay, so this is how it looks like untuk conventional type of galvanometer. Okay, so we have different types of galvanometer. The purpose is sometimes to measure the current and sometimes they can measure also the voltage, but normally they refer to current. Okay, so basically for the galvanometer, they use the mirror and also the light beam. And then this is all the generations of the galvanometer. Okay, so this is the astatic galvanometer. This is the de-ensemble galvanometer. Okay, so astatic mirror galvanometer is used to measure the current intensity. Stands on a circular wooden basis with 3 leveling screws. So a mirror is placed at half height of the thread and is developed by Johann Christian Poggendorff in 1826. So this galvanometer is also, they call it as the spot galvanometer. So the operation occur when the current that must be measured pass between the two magnets and makes them turn in the same direction. So through the rotation amplified by the mirror, we can obtain the current intensity. So you can see here, there is a small mirror that is placed into the in between of the thread. Okay. And then we have a de-ensemble also to calculate the intensity of current. And then the Becker, Siemens, and Hawks used in the Siemens pump. So this is the okay. Then we have a Thomson galvanometer. So instead of one single galvanometer, we have this type of galvanometer. So different manufacturer, they have their own design of the galvanometer, but at the end, the purpose of the design is always the same, which is to measure the current. Okay, so here they use a lamp with a very brilliant flame is placed behind a screen. Okay, so through a slit, it sends a light beam onto the mirror that reflects it on graduated scale placed at a distance of 60 centimeter from the galvanometer and enhance the very small deviations. Okay. Then we have a Mecker by Mac Edelman Munich. So this is their moving coil galvanometer, which is also a measured current intensity. String galvanometer is also manufactured by the Max Edelman Munich. They use a detector to which is placed between the two magnets. Okay. So from one side, we have a source that sends a light beam, which arrives on the wire detected by a microscope placed on the other side of the device itself. Okay, so this is the tangent galvanometer. They follow the tangent rules. Okay, so if the current passes through the circuit, the needle is subject to a couple of forces that tend to dispose it perpendicularly to the turn. So the couple intensity depends on the current intensity that passes in the turn. Okay, so this is how it looks like. And also the important part in the design of the galvanometer, they have what we call as the adjustable shunt resistor. Okay, so this is your galvanometer. So this is where you need to place your shunt resistor to control the excessive current that pass through the galvanometer. Okay, so make sure when you do the measurement, you put a proper galvanometer for measurement. So if too big current enter the desired galvanometer, without the shunt resistors, it will damage your meter. Okay. So here, okay, we have a basic of instrument. Then we have another type. We have a thermocouple RF emitter. Okay. So this is the type of the instruments that can be measured by zero positive value. Okay, so cannot be reversed. They don't have any negative value. So the task for this thermocouple is used to measure the emitter by using the changes of the thermal itself. Okay. And then we have a zero DC, zero center DC micro emitter, where you can have a positive and also negative. So this one is to measure a very small value of current. As you can see, this one is microamp. So if you are using, if your circuit is more than microampere, no need to use this type of instrument. Okay, you use the proper instruments when do the measurement. And then we have a edgewise panel meter movement. So instead, the reading is up here. So this one, the reading is at the edge. Okay. So it is also available in both zero, or sometimes it can have a center zero model also. Okay, so this type of panel meter, it has an internal photoelectric alarm sensor that indicate when the pointer deflection is below or low limit or above height limit. Okay. And then we move on to the deflecting meter movements, AC and DC. Okay, so you have this is how the alternating current looks like. Okay, so this is the sine wave, this is a square wave, and this is the triangle wave. Okay, so in your this one can be viewed when you are using oscilloscope. So later, maybe during your second semester, or I don't know how they arrange for your lab number one, you will be able to go to the lab and do the measurement both by using the emitter and also by using the oscilloscope. Okay, so maybe in your last part of your course for the KNR1042, you will work on the use of the oscilloscope. Then you can see how the sinusoidal wave looks like, how the square wave looks like, and how the triangle wave looks like inside the oscilloscope. Okay, so this is for the alternating current, or sometimes we refer to as the AC. Okay, so the alternating current, they have what we call as the peak to peak. This is your peak. Okay, so you need to measure by the amplitude, and this one is your time. Okay, so this is the amplitude, is the voltage. Okay, so we have what we call as the root mean square. Okay, so root mean square is the value of the root mean square of your this measurement, where you have 0.707 multiplied by the peak value. Okay, and also for the average, we have 0.637 multiplied by the peak value also. Okay. And then the peak to peak will determine the total amplitude of your signal. Okay. So this is all the formula for the square wave, and also this is for the triangle wave. So normally we will do the calculation for the alternating current for the sinusoidal wave types only. Okay. So here is the movement of the current. As you can see, your current will move from 0. It goes to the highest point, where this is what we call as the peak. And then it goes down again to the 0 point. And here is your negative part. It will go down to the same peak as your positive part, and then goes back to the current, to the center of this axis. So in here, in here, there is no current exist. So first, the current is highest at the positive part, goes down, and then if we go to the negative part, the highest of negative part, and then it goes up until 0. So this one will oscillate until the time that you specify in the measurement itself. Okay. So here is what we call as the single phase AC. Okay, so this is a full wave, single phase. And then single phase half wave rectify. So rectify meaning that they consider only the positive. Okay, where your negative is neglected. So this one is the time between the rest of your first signal to the second signal. Okay, then we have a single phase full wave rectify AC. So meaning that the second wave here, it will be pulled up to become a positive value. Okay, and then this is a three-phase AC. We have one oscillation, second one, we have another one, 0. Okay, so this is why they call it as the three-phase. Then this is a full wave rectifier. So all the negative part will go up to the measured to the positive part. Okay, so okay ke? Okay, so this is the calculation that I mentioned just now. So average and RMS value, how to calculate if you are given peak to peak sine wave. Okay, so we have average full wave, how to calculate it. Okay, so this one is for the half wave. Okay, so 5 principal meter movement used in AC. We have electrodynamometer, ion band, electrostatic, thermocouple, and diarsonval with rectifier. Okay, so this is all the applications of meter movements in all different types of meter movement. Okay, so you can see that either they can be used by DC or they need to be used by AC. Okay, for example, we have a diarsonval. You can see that if you want to use as an AC devices, you need to have a rectifier. Okay, so this is most widely used meter movement for measuring direct current or voltage and resistance. Okay. So the PMMC instrument on AC must be polarized. We need to have terminals of positive and also negative value. Okay. So it must be connected correctly for positive with the deflection to occur. Okay, so when an AC with a very low frequency is passed through a PMMC, the pointer tends to follow the instantaneous level of the AC. So as the current grows positively, the pointer deflect increase to a maximum at the peak of the AC. Okay, so this is what I mentioned just now lah. If your current's highest, you have the maximum peak, and if your current is lowest, you have the maximum negative value. Okay, so we can have 50 gigahertz, 50 hertz or higher frequency supplies. So the damping mechanism of the instrument and the inertia of the meter movement can prevent the pointer from following the changing of the instantaneous level. So the average value of purely sinusoidal AC is practically zero. Okay, so kalau dia practical lah. So sometimes we have a value is because of the environment and also because of the apa tu yang your temperature, your room, and also the persekitaran of your lab. Okay, your instrument also affect the calculations of the results and everything. Okay, so it is important to note that although a PMMC instrument connected to an AC supply may indicating a zero, there can be actually very large RMS current flowing in its coil. Okay. So there are two types of PMMC that use in AC measurement. We have half wave and also full wave rectification. Okay. So moving coil meters, the design of a voltmeter, ammeter, or ohmmeter begins with a current sensitive element. So we are using a moving coil current detector. We call it as a galvanometer. So since the modifications of the current sensor are compact, so it is practical to have all three functions in a single instrument with multiple range of sensitivity. Okay, so we have a voltmeter, ammeter, and ohmmeter. So practically and conventionally, previously we have a voltmeter, ammeter, and ohmmeter individually. Okay. Where for voltmeter, you need to find the voltmeter to only measure the voltage. Same with the ammeter, only measure the current, and ohmmeter is only measure the resistance. Okay, so instead of individual design of the ammeter, voltmeter, and also resistance, we ohmmeter, we put it in a single range multimeter and control it by using a galvanometer and also the resistance of galvanometer. So we call it as a multimeter. Okay. So this is how it looks like for the calculations of voltmeter. Okay, so measures changes in voltage must be connected in parallel. So you need to remember, sometimes students, they have problems when connecting the voltmeter. They put it apa tu? Like this. You just put here and here without disconnecting. Sometimes you don't need to put, you need to parallel, put it in the parallel. So we have a circuit one. This is you punya wire to connect with the resistant. So meaning that the current, the voltage will flow from here is the same with the voltage that flow through your voltmeter. Okay, so must be parallel. Okay, kalau you letak dalam, you putuskan the wire, you letak selari dalam you punya circuit, it's wrong, tak sama. Okay, so voltage contoh kan, kalau we have A1 here and A2 here, so if you want to measure A1 and A2, so you need to have a parallel connection. Okay, so you cannot put, you cannot just simply put you punya connector in the middle of the circuit. Okay. So this is how it designs for the voltmeter design. We have what we call as the IG, which is the current that flows through the galvanometer. Okay. So why it is necessary for the voltmeter to have a very resistant so that it does not have an appreciable effect on the current or voltage associated with the measured circuit. Okay, so why? So this is the solution here. So in order for you to have a voltmeter sensitivity, you need to have a voltmeter that can have a very low sensitivity. So if you have a very low sensitivity, you can get a good result. Okay, and also you can get a determine of the reciprocal of the full scale current. Okay, so it is very important for the voltmeter to be a very sensitive devices. Okay, so this is emitter. So sometimes students they confuse with the calculation of the ohmmeter and voltmeter. So voltmeter must be parallel, while for the emitter must be in series. So you need to cut your connection here and then put the emitter in between so that your current will flow directly from here through your emitter and goes to the resistant. Okay. So this is how it looks like kalau letak dalam water meter tu lah. Okay. So must have a very low resistance to avoid significant alteration of the current when you want to do the measurement. Okay, so sometimes student they put the voltmeter, the emitter parallel. So kalau parallel, dia punya current tak sama lah. Okay, and also you punya circuit is short. Okay, so instead of you punya current, okay, kalau you letak parallel kan, you letak kat sini. So instead of you want to go jalan yang ada halangan ataupun you nak pergi ke jalan yang tak ada halangan. So better you pergi jalan yang tak ada halangan kan. For example, kalau you punya emitter, dia have a very low resistance. Okay. So meaning that this one will not give you an accurate result. So current untuk parallel is not the same. Current untuk series is the same. Kalau letak emitter sini, emitter sini, emitter sini, emitter sini, emitter sini is the same. But kalau you letak emitter in parallel, is not the same lagi. Okay, so dia akan you have a wrong result, and then sometimes you punya circuit akan short. Okay, and also sometimes dia akan rosakkan dia punya emitter if the current is too much for you. Okay. So this is how it looks like inside the emitter design. Okay. So that's why for the emitter design, they need to be put in series with your circuit. Okay, so then we have the ohmmeter. So the standard way to measure resistance in ohms by using the Ohm's law, V is equals to IR. Okay, so V is your potential in volts, I is your current, and R is your resistance. So need to remember this Ohm's law. Okay, then we have a moving iron repulsion type instrument. So this moving iron is also what we call as the PMMC with the movement. Okay, so this is how it looks like. Instead of a single coil and single pointer with a counterweight, they have what we call as this one. They have a wire coil and they have also a needle with no counterweight. Okay, so we have meter terminal connections that connect through directly with the devices. Okay. So we have a controlling device, a spring will control and gravity will control. Damping services, air dashboard damping is used. Operating device is between positive to negative. We have positive only, depend on your punya instrument itself. And the construction is a piece of soft iron is fixed inside the coil former, and another piece is free to move on a steel spindle. The repulsion between these two pieces give the deflection of the pointer. Okay, so this for the zero center movement, we'll have pair of metal connection terminals on the back of current to enter and also to exit the instrument itself. most are polarity sensitive. So some have needle that is spring-centered and some can be at a 0 point where you have positive measurements only. Depend on the instrument itself. Okay, so a movement is the display mechanism of a meter. So electromagnetic movement works on the principle of a magnetic field being generated by electric current through a wire. So examples of electromagnetic meter movements include the de-ensemble, Western and iron band designs. So electrostatic movement work on the principle of physical force generated by an electric field between the two plates. Okay. So here is the permanent coil magnet moving coil. So to increase the accuracy and efficiency of this meter, we use two types of technique. First is by placing the iron core inside the coil to concentrate the magnetic fields. And then we provide a curved ball that are attached to the magnet to ensure that the turning force on the coil increase steadily as the current increase. So this is the de-ensemble movement. So there are two types of problems that exist in the de-ensemble meter movement. So first is the permanent magnet moving coil meter movement used is in most electrical and electronic meters. So why we need to have a de-ensemble? Okay, so what is the important criteria in the design of the de-ensemble is in terms of the magnetic field is also generated around the coil, and the attraction of this field with the permanent magnet cause the coil to move. Okay, so there is normally the same as long as how accurate and how the movement of magnetic field of each of the device. But the basic is they need to have the magnet, the coil, and everything to operate it. Okay, so what are the three functions of the hairsprings in a de-ensemble meter movement? So the three functions of the hairspring is first is to make sure that the pointer will return to its rest position where there is no current flow, to oppose the coil movement and when there is current flow, and to provide electrical connections for the ball itself. Okay, so this is the advantages and disadvantages of the PMMC. So they have a low power, scales are uniform, a very high torque, and also a torque over weight ratio. They can be modified with the modifications of the shunt resistance value, and they have no hysteresis loss. But the problem of the PMMC is sometimes in terms of the control springs, aging of the control springs, and also the permanent magnet. Okay. And then also they have a delicate construction. Okay, so this is all the disadvantage for the PMMC. So we have also the electrodynamic or dynamometer, which have a moving coil production only, but the moving coil is not permanent. Okay, they use it another fixed coil, so it can be used either as an emitter or voltmeter. So such instruments are free from hysteresis and eddy current error. Okay, so they have also the low sensitivity. Okay, so this is the example of a wattmeter used to measure electric power. Consists of a pair of fixed coils known as current coil and movable coil, and also known as the potential coil. Okay, so this is the movable coil, current coil. Okay, consists of the two circuits, either of which will be damaged if too much current is passed through them. Okay, so why two circuit in the design of the wattmeter? Okay, so to control the wattmeter to have overload current and also to avoid the damage for the wattmeter and also to avoid the burning of the inside of the wattmeter itself. Okay, so thus a low power factor circuit will give a very low reading on the wattmeter, even when the current and potential circuits are loaded above the maximum safe limit. Okay, so that's all for this chapter. So this one is only theory. So you can go to the ellipse. You can see the exercise for this chapter is only for you to distinguish what are the three forces that need to be exist during the measurement. So we have here is the deflecting, this is the controlling, and this is also the damping. So please try to do it and then put the figure inside it also for you to be able to remember how does the controls of how does the forces looks like. Okay. And also we go back to the ellipse. So I will give you a letter on Thursday. The quiz on Thursday lah. Okay. And also maybe on Thursday or yeah. Any question? So the one that activities that I put in the ellipse for last week.
Madam,
Hmm?
can you upload the answer for activity 3 and the recording to the Elite?
Activity 3, the measurement gap.
Yeah.
Yeah. Okay. So this is previously I give to you all the exercise for number 3, but I cut it into a smaller one. But normally the question will play around with this one. Okay. So, sama tak? So exercise 4. So, this one ke? Kan yang ni dah. This one dah. Yang belum is this one boleh buat sendiri. This one pun simple. The one here. This is the this one. $500. This one is a page of resistor. Dah buat tu yang is your answer for question number 1. 500 ohm resistance with accuracy of plus minus 10%. For the question, sometimes they can twist the question, and then as long as your answer is good. The current was measured by an analog instrument on 50 milliamp range with an accuracy of plus minus 3% of full scale. So calculate the power dissipated in the resistor and determine the accuracy of the result. Dengar kita pula yang buat tu.
Yeah, madam. But question 3 and 4 don't know how to do.
3 and 4 dah ke? Belum ke? So what is your answer for question number 1? Okay. Disambungkan 500
Plus,
resistor.
my question 1 answer is
What you get? 0.05 plus minus 40%.
yes, yes, madam. Same.
So the number 3, you confuse with number 3 and number 4.
Yeah.
Resistor of 800. So you have resistor, you need to find their absolute error, 3% of 800 for these two resistors. Have a resistor in parallel also. 2. So this one you need to calculate the total resistor. First, the series resistor, then the second is the parallel resistor, then total up everything. Yeah, so here is another example. Saya tak buat yang record. Try to see this one first. Ada tak yang sama? Screenshot. Try to check here dulu. This a batch of resistor. Calculate. Try to check this one. This one is another exercise. Ini how they do it. Okay, for question number 1, you are given 2 resistors. First resistor is 330 ohm with accuracy of plus minus 5%, and the second one is the same value of the resistor plus minus 10%. So you need to calculate the maximum and the minimum absolute resistance. Okay, so first for resistor number 1, okay, so we write R1 330 plus minus 5%. So 5% out of 330 is equals to 5 divided by 100 multiplied by 330. So you have around 16.5 ohm. So this is the absolute value. So we have 330 ohm plus minus 16.5 ohm. So R1 maximum is equals to 330 ohm plus 16.5 ohm equals to 346.5 ohm, and R1 minimum is equals to 330 ohm minus 16.5 ohm, which is 313.5 ohm. So next one is the R2. We have 330 ohm plus minus 10%. So 10% from 330, we have 10 divided by 100 multiplied by 330. So you have around 33 ohm. So this is the absolute value of the resistor number 2. So R2 can be written as 330 ohm plus minus 33 ohm. So R2 maximum is equals to 330 ohm plus 333 ohm. So you have 363 ohm. For R2 minimum, so you have 330 ohm minus 333 ohm. We have 297 ohm. So this is the answer for question number 1. This one is another one. It's the same semua. Saya ada banyak. For this one, here is second one. For question number 2, try to get the ideas on how to do your exercise. And then these 3 resistors are connected in series. So we have resistor number 1, R1, R2, and R3. So it gives that the value of the resistor is the same with the problem number 1, which is 330 ohm. So the first resistor will have the tolerance or the accuracy of 5%. And the second one, we have 330 ohm plus minus 10%. And then R3 is the same tolerance with R2, we have 10% also. So in order for us to do the summation, so you need to know that for summation plus or the summation of 2 or more quantities, we need to have an absolute or what we call as the real value of the error, so not in percentage. So you need to remember here. So then we need to change the value of R1, R2 and R3 into a absolute value. So we have R1 is equals to 330 ohm plus minus 5%. So 5% out of 330 ohm is equals to 16.5. So we have R1 is equals to 330 ohm plus minus 16.5 ohm. So R2 is 330 ohm plus minus 10%. So we have 10% out of 330. So we have around 33 ohm. So R2 330 ohm plus minus 33 ohm. So R2 is equals to R3. We have the same value of the resistor and also the tolerance value. So next we have the summations of the resistor. So R1 plus R2 plus R3 is equals to 330 ohm plus minus 16.5 plus we have 330 ohm plus minus 33 ohm plus 330 plus minus 33 ohm also. So first you need to select the value of the resistor first, this one, and this one. So you need to add up this one, and this one first, then you add up the errors, this one and this one. So next you will add up this one. Okay, so from here you know that your answer will be 330 plus 330 plus 330 plus minus, this is your error. Okay, so you have 16.5 plus 33 plus 33. Okay, so here this is the R1 plus R2 plus R3, and this one is also the errors of each of the resistor. Okay, so from here you total up, you get your answer 990 ohm with the error of around 82.5 ohm. Okay, so this is your R total. So R total maximum is equals to 9990 ohm plus 82.5 ohm. We have 1072.5 ohm, and RT minimum we have 990 ohm plus minus 82.5 ohm. So you have around 907.5 ohm. So this one is the answer for question number 2. So you have RT maximum is equals to this one, and the RT minimum is equals to this one. Okay. For question number 3, so we have 4 electronic circuit with a DC power supply. So the currents is given to you as I1 is equals to 37 milliamp, and then I2 is given as 42 milliamp, I3 is given as 13 milliamp, and I4 is given as 6.7 milliamp. So the first two are with an accuracy of plus minus 3%, and the other two are measured with 1% accuracy. Okay, so determine the I total maximum and I total minimum of the total supply current. So this one is you need to find. Okay, so first you change this value into real value. So you have I1 is equals to 37 milliamp plus minus 3%, which is 3% out of 37 milliamp. So you have around 1.11 milliamp. So next one, I2 is 42 milliamp plus minus 3%. So 3% from 42 milliamp. So you have around 1.26 milliamp. So the third current is 13 milliamp plus minus 1%. So 1% from 13 milliamp. So you have around 0.13 milliamp. And the last one, we have I4 is equals to 6.7 milliamp plus minus 1%. So you have 1% out of 6.7 milliamp. So you have around 0.067 milliamp. Okay, so next is total up the current. So I total is equals to I1 plus I2 plus I3 plus I4. So you have 37 milliamp plus minus 1.11 milliamp plus, this is I1, so 42 milliamp plus minus 1.26 milliamp plus 13 milliamp plus minus 0.13 milliamp plus 6.7 milliamp plus minus 0.067 milliamp. So from here you need to total up the current first. This one, this one, this one, and this one. Then you total up the error. This one, this one, this one, and this one. Okay, so the current will be 37 milliamp plus 42 milliamp plus 13 milliamp plus 6.7 milliamp plus minus the error. So you have 1.11 milliamp plus 1.26 milliamp plus 0.13 milliamp plus 0.0067 milliamp. Okay, so this is the current, and this will be your error. Okay, so you total up, you have around 98.7 plus minus 2.567 milliamp. Okay, so T max is equals to plus 2.567, which is equals to 101.267 milliamp. For IT minimum, we have 98.7 plus minus 2.567, we have 96.13 milli M. So this is the final answer for maximum and minimum current. Okay, maximum and minimum current for question number 3. Okay, so is it okay for you all? This one is normally students they can instead of calculating one by one, some of them just calculated directly, but normally to be safe, better you need to check, you convert it to the real value first before you go in detail of the calculation. Okay? Okay, Kerr? So this
Doctor,
one, normally the example is most on the summation.
doctor,
Hmm?
do you have one that has problem regarding parallel resistors?
Parallel?
Ah,
Oh, belum lagi.
oh,
This one is all this answer here yang ada kat sini lah. So untuk parallel, macam so, okay, so for the parallel questions, let me see here. We have number 3. Two resistors are connected in series and two resistors are connected in parallel. So calculate the total resistance. Okay, so to answer the question, the rest saya akan bagi on Tuesday. So I will go through this number 3 first. Tak ada bawa tu. Okay, so you have resistor 1 is 800, resistor 1 is 800. We have R series is equals to R1 plus R2. Okay, so we all know that for the summation, for the real value, for the summation, you need to have a real value of the R1. Okay, so you can see that here we have add up everything. We have 100 ohm plus minus. We have around 48 ohm. Betul ke? Kita buat. Tahu kan? So first untuk satu resistor, dia punya error is 24. 3%, which is 3% out of 800 ohm. So we have around 24 ohm. So the error for the summation, we need to plus together. So you have error of R1 plus error of R2. We have 24 plus 24 is 48 ohm. So settle with the R series. Then you need to go to R parallel. Function untuk yang series.
Faham, madam. Okay, then you go to the parallel. So the parallel is the combination. Kalau you tengok kan, the R parallel is equals to R3 multiplied by R4 divided by R3 plus R4 kan. You tahu ke formula untuk kira parallel? parallel resistor, if you have two parallel, dia adalah, saya tak ada pencil. Dia adalah lebih kurang. So 1 over R parallel is equals to 1 over R1, R3 lah kita cakap, plus 1 over R3, R4. So since this one is two resistor only, so you summarize it everything from here, you can get your formula of RP is equals to R3 plus, R3, R4, R3 multiplied by R4 divide by R3 plus R4. So this is your formula. Okay, so you can find your parallel resistor directly, which is around 6 ohm. 6 ohm tu biasalah 6 ohm. But the problem is when you finding your error. Okay, so you need to put it step by step. So since this one, you can see here, yang ni adalah multiplication, and we have division, and this one we have summation. So this one in percentage, this one is in percentage, and the bottom one will be in real value. Okay, so you need to do it part by part. Okay, so first you have the error. So this one untuk parallel resistor is okay. The problem is you want to calculate the punya error. So then we have the percentage error of RP is equals to plus minus of the percentage. We have 5%. So depend how are you going to answer the question. Your answer of error depend on your method. Okay, so 5% plus 5%, since this is the error for R3 and R4. Okay, so we have divide it. Bear in mind, this one is the real value. So you need to change to real value. You have 0.6 plus 0.6. Okay. Okay, you do everything. You find your answer is around. The above one is 10%. Okay, so yang bawah is we have 1.2. This one you need to have R3 plus R4 value juga. So R3 plus R4 value. So your R3 is 12. We have 24 ohm. So we have here is, at the end, later you have 24 ohm plus minus 1.2 plus minus 1.2 ohm. So this is real value. You need to tukar balik kepada percentage sebab you nak buat division. Okay, so tukar balik, you have 5%. Okay, 1.2 out of 24 ohm is 5%. Okay, so you have 5%. Then you have this one, 5%, 5% plus this value. Okay, so you have, at the end, you have 15%. So this is for you punya error for the parallel yang ini. So for the parallel is the RP equals to 6 ohm plus minus 15%. Betul ke? Okay, so you have 15%. Then you go back lagi to calculate the series, the parallel and also the series. You add up this one plus your series resistor, your parallel resistor. Add up all together. So you have R total is equals to 1606 ohm. And this 48 ohm, you need to maintain it. This one, the 5% of RP, you need to change it to the real value sebab you buat summation. So you have 48 ohm. Okay, so plus what is 5%? 6 apa tadi? 6% plus minus we have 15%. 15% daripada 6 ohm. So this one is around we have 0.9. Kat sini 0.9. This one is also 0.9. So at the end, so this is your 1609, 1606 plus minus. Your error is 48.9 ohm. So it's either for you want to check to change it to percentage value is also okay. You want to stick until here pun also okay. But sometimes the question they will ask you again what is the maximum and minimum. So maximum you just add up 48 ohm. The minimum you just minus 48.09 ohm. Okay, so this is their punya total resistance value and this is their punya measurement accuracy. Okay ke?
Okay, madam.
Okay,
Okay,
doctor.
Okay, so the rest we'll discuss and continue later on on Thursday lah. Okay. So you check also this exercise, maybe you snapshot lah. Ada ke dalam e-lab saya this exercise?
Tak ada.
Tak ada.
Tak ada.
This saya upload. This one is quite the same with this one. This one is a simpler. Saya dah buangkan soalan yang tak berkaitan. Tak apalah, nanti saya upload this one.
Okay,
Okay.
the exercise only kah, doctor?
The exercise only. And the other one is yang apa tu? Yang deflecting meter tu lah. We have 2 exercise today. No. One only. The previous one is just to strengthen your understanding on this one.
Okay. Doctor.
Tak. Kena ni setak. Apa ya?
Just now earlier you said we have quiz on Thursday kan?
Nanti saya akan
Will
add up semua.
is it going to be objective or subjective?
Subjektif je. You akan main sama ada visualize kot saya rasa. Or Kahoot.
Okay.
Cari tu juga.
Okay.
Okay ya. So,
Okay.
apa lagi saya masukkan. Okay, so any more question? So if no more question,
Sorry, the quiz
Okay.
would be on this last chapter that we just did.
of the summation of these two, 1 and 2. Tapi I think
Okay.
no more calculation, just a theory only.
Oh, theory. Okay.
Mm.
Okay. Thank you.
Okay. Any question lagi ke? Yang lain? Sebentar. Okay, so if no more question, with that, thank you very much. I will see you on Tuesday lah. Sekejap, saya buka balik attendance. Okay, so thank you and Assalamualaikum.
Thank you, madam.
Thank you,
Madam.
Thank you, madam.
Thank you, madam.
Thank you, doctor.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Thank you,
Thank
doctor.
you.
madam.
Thank you, madam.
Thank you, madam.
Thank you, madam.